This is the experiment on reflection and refraction. First, let's deal with the physical principle of reflection. Reflection occurs when I have an incident ray. Remember, I always measure my incident ray, the angle for my incident ray, from an axis that is perpendicular to the optical surface, to the reflective surface, your mirror in this case. So I have this ray that is incident onto the surface. That's called theta I, the incident angle. And then it is reflected in such a way that the reflected angle is equal to that incident angle. Remember, this was one of the properties of light that Isaac Newton first observed, which led him to believe that light behaves as a particle, and indeed it does behave as a particle. Now, the way that we determine the image in this object, let's say that this ray originated from a star or some object. We call this distance the object distance. So P is the object distance. The object distance is the distance from the reflective surface to where the object is. We want to figure out where is the image. Now, we determine where the image is by imagining an eye, an all-seeing eye right here. So there's my eye, and it sees the reflected ray. And if it traces this ray back, then where the ray goes is where it sees the image. So I'll talk more about this in a bit, but this is the image, and where it sees the image is called the image distance, and we usually call this Q. Now, typically, Q is the image distance. For mirrors, the space behind the mirror is a virtual space. And we talk about distances in that virtual space, they will be given a negative value. So the image distance then is equal to the negative of the object distance is equal to the negative of the image distance. So for example, if the object is 2 meters in front of the mirror, then we would say that the image distance is negative 2 meters. That's true for flat mirrors, that the image distance is always equal to the negative of the object distance, and vice versa, that the object distance is the negative of the image distance. More about that as we get into the practical part of this lab. Now let's look at refraction. Refraction has two implications, or two implications, I guess, that as I have a light ray move from one medium to another, let's say that it's moving from air to glass, we can talk about the index of refraction in this. The index of refraction is the ratio of the speeds. The speed of light in a vacuum, this is in a vacuum, and then this is the speed of light in some medium. And we'll say that the speed of light in air is the same as that of a vacuum. Now, as an aside, that's not really true. The index of refraction for air is not actually equal to 1. It's actually like 1.000 something. It's a number that's really close to 1, but not actually equal to 1. But nonetheless, we'll say that it's equal to 1. And the index of refraction for glass, I'll call this N2, is about equal to 1.5. So the index of refraction for air is equal to 1. The index of refraction for glass is equal to 1.5. Now, I can calculate what is the change in speed of that is going to be equal to c divided by n. So the speed of light in a vacuum, or almost in air, it's not exactly 3 times 10 to the 8th meters per second, but in a vacuum it is, divided by the index of refraction, which is 1.5. Notice the index of refraction, which is a ratio of two speeds, has no units. So the velocity of light in glass then would be 2 times 10 to the 8th meters per second. So light slows down when it moves from an area with a low index of refraction to a higher index of refraction. And the opposite would be true as well, that as light moves from a high index to a low index, it's going to speed up. Now, that was when the light doesn't have an incident angle, or it's perpendicular to the surface. But now imagine, let's say I have N1, N2, and we'll take the example of glass again as it's moving from air to glass. If I have a light ray that is incident on this surface, and we'll call this theta 1. It's going to be the incident angle. As it's incident on that surface, it will bend. And the reason it's going to bend, if I imagine my wave fronts coming here, the reason that it bends is because part of the wavefront is moving at a faster or slower speed than the other part of the wavefronts. So as this part of the wavefront moves into the glass, it's going to move more slowly than this part of the wavefront. So I'm going to be fast over on this side and slow over on this side. That's going to cause this wavefront to move in that direction, which will cause the light ray to bend towards the normal. And this is going to be my angle theta 2. That is the refracted ray. I can calculate these angles. N1 sine theta 1 is equal to N2 sine theta 2. If I'm moving from 1 to 1.5, n equal 1 to 1.5, that means that the angle theta will decrease, right? It goes from a big angle here to a small angle. And then if I move from big to small index of refraction, the angle theta will actually decrease. So if I'm moving from n equal 1.5 to n equal 1 or some other, decreasing value, the light ray comes in here and it moves in this direction. By the way, this is the scenario where I have total internal reflection. If this angle theta 1 gets to be small enough, that would be big enough, that would be the critical angle, which would cause total internal reflection. There's one other theoretical thing we want to talk about, and that has to do with a prism. The prism looks like this. In this lab, you'll be dealing with an equilateral prism, so you can determine what is this angle A. I'll give you a hint. It is 1/3 of the total number of degrees in a triangle, which of course the triangle has 180 degrees in it. If I have a ray that comes into this triangle, let's say that I'm going to draw my optical axis here, which is perpendicular to the surface. I have a ray that comes in here. I'll call this theta 1. It's going to bend first towards the normal. Right? This angle is smaller, and now over here, as it moves from a high to low index, it will bend away from the normal. So my light ray looks like that. The angle that I'm really concerned with in this is I want to know what is the deviation angle. So if I take my incident ray right there, and then I take my refracted ray right here, I want to know what is this angle D. Sorry, I need to pause for a second. So you want to measure that deviation angle for different angles of incidence. Remember, that's my angle of incidence. In fact, if I plot the angle of deviation, D, versus my angle of incidence, it's going to look something like this. So there will be some minimum deviation angle, which we'll see right here. So this is what's going to be dm. Basically, you're going to measure several deviation angles, and you're going to find out what is the smallest of those deviation angles. Now, given that, I can then calculate what is the index of refraction for this prism. And n is equal to the sine of a plus dm. A is the prism angle, dm is the minimum angle of deviation. This is all divided by 2, divided by the sine of A divided by 2. So this is equation 5 in your lab manual. So you'll use the parallax method in order to measure this deviation angle. Before we get into that, I want to talk about a protractor. So this is a protractor. You will need to use a protractor. If I have an angle, let's say I have an angle right here, I want to know, say, what is this angle right here? The way that I find that is I take the difference between 90 and what's that, like 49. So this angle will be theta equal to 90 minus 49 is 41 degrees. Or if I'm trying to measure this angle, I'll go from 0 to, that would be 49 degrees. Okay, it's important that the vertex of where your angle is, where those two lines come together, that it goes in this little point right here. I think that our protractors actually look just like this one. So you might have been sometimes to use a protractor. If you're uncertain about how to use it, then please ask your instructor. So with the parallax method, in the first part, I'll show you how to set this up in the lab, but in the first part, you're going to have some pins set up. I'm from Mississippi, so pin and pin sound the same to me. I mean a pin, like one of those sharp, pointy things that you use for, I don't know, holding cloth together. You're going to put pins here that will fall along the incident ray. So this is our incident ray, theta I. All right, these are pins. Those are pins. Anyway, you get the idea, the sharp pointy things. So you're going to put your pins right there, and they will be along the ray, the incident ray. Then you're going to look in the mirror right here. This is your eye. You have big long eyelashes. You're going to look off to the side until you see images of the pins in the virtual space. So this is the virtual space, the space behind the mirror, and you're going to place additional pins so that they all line up in a straight line. So when you're looking at this pin right here, you won't see this one or this one or this one. Now these two, of course, are images of the actual pins, which are over here. And that's called the parallax method. Parallax, that these things all line up in a straight line. And by doing so, you can then draw where is the reflected ray. So this is where my reflected ray is, theta R. So that's in part 1A. Now in the second part, we want to move one of these pins. So I'm going to do this in green so it stands out. We're going to take a pin. Well, that's not green. We're going to take a pin and put it right there. Actually, that's not a very good spot. We're going to take a pin and put it right here. Then I'm going to do a similar thing where I put my eye over here and I look for places. I'm going to go ahead and draw my incident ray. It's going to look like that. Because see, look, I have a pin there, and then I'm using this pin as well. I'm drawing a line through where those two pins are, and they create my incident ray. And then I look for the images of those pins. One of them is going to be in the same place as the first one, and now this one is going to be like right here. It'll be somewhere different. And then I line this up with my eye and place two pins here and here so that they block the image of the other pins that we had. And then I can draw another reflected ray. Now notice this is a separate ray, but they have this point in common. What that allows us to do is to figure out where is the image of this pin, because it is where these two lines cross. Then I can measure this distance, which is P, and then I can measure this distance, which is Q. Q is the image distance to the image for this object. Now, it should be that P is equal to negative Q, and we want you to find the percent difference between these two values. Of course, take the absolute value of the measurements. It's a similar thing for the glass slab. So what you're going to do is measure. You're going to have a glass slab right here. Actually, I'm sorry, hold on. Actually, before I get into the glass slab, let me just go back and make something clear. You're going to put your mirror right here, and you'll draw a line where your mirror is. So your mirror is going to go like on the sheet of paper, and you'll stand it up. I'll show you this in the next video, but draw a line, trace a line where your mirror is. And then also make sure that you, oh no, never mind. Just draw a line where the mirror is. Now, moving on to the glass slab refraction. I actually drew this incorrectly, so let me draw it again. You're going to get a glass slab, and it's going to be square, flat, maybe a centimeter thick and a few 4 or 5 centimeters on edge. What you're going to do is you're going to take your sheet of paper like this, and you're going to trace around the glass slab like that, so that on your sheet of paper you have an outline of that glass slab. Then you're going to take 2 pins here and here. For example, you're going to trace a line so that it goes here. That's going to be your incident angle. This will be theta I. Now, as they move into this glass slab, they will move closer to the axis, and then over here, they're going to move out like that. Now, you're going to use the parallax method in order to draw these lines. And the way that you're going to do that is you're going to have your eye, that is not right, have your eye right here, looking for the image of these 2 pins on the opposite side. And when you find the image of those 2 pins, you're going to put pins here and here so that they all line up. But if you notice, these don't line up, that these are actually not line up because you're not looking at the actual pins, you're looking at images of those pins. But after you do that, then you can draw this line, you can draw this line, and then you can connect those 2 lines here. Let me blow this up. I'm going to redraw it. So this is my glass slab, and then this is my perpendicular line. This is going to be one of the angles. We'll call this the angle of incidence. And then this angle right here is the refracted angle, which is theta r. Or I think in your lab manual, actually, this is called theta 1 and this is called theta 2. So you'll measure theta 1 and theta 2, and then you also want you to measure the exit angle, which is going to be this angle. That is your exit angle, which is referred to in the lab manual. Now you can calculate the index of the refraction of glass by this way: n1 sine theta 1 equals n2 sine theta 2, where n1, you'll take that equal to 1, that's for air, and then n2 is, well, that's what you want to know. But you have your theta 1 and your theta 2 right here. And then once you find that n, your professor would tell you, but I think we're using 1.5 for the index of refraction of glass. Yeah, that's in your lab manual. Now, for the prism, you're going to do something similar. This was a little bit trickier, but you'll get the hang of it by the time you get to it. You'll take your prism, and you're going to take 2 pins, and put them right here. We give you some prescribed angles for this, so you'll start with an angle of incidence of, say, 40 degrees. And then you'll do this for 45, 50, and 55 degrees. And then, we'll look over on this side, and we'll place pins here and here. That means that my refracted angle comes out there. Once I have those 2 lines traced, then I can trace this line. Okay, and so I know that my light ray travels through the prism in that way. That's true for the glass slab too. That the first thing that I do is draw this line, then I put the pins over here and I can draw this line, and then I can draw the line through the middle of the glass. So, or not through the glass, but on the paper, and that represents the ray that goes through the middle of the glass. The ray that goes through the glass. Then, after measuring theta I, or the deviation angle for those different theta i's, there's d, theta I. You have 4 different angles. Probably this is going to be somewhere in between here, so we figure out what is that d min, what is the minimum value for that deviation angle. And you can use equation 5 to calculate the index of refraction for that prism.